Okay, hello, my name is Tarin Paz-Kagan, and I will present today the topic of site-specific nitrogen management in citrus orchard to minimize nitrogen pollution. So usually estimating crop nitrogen status to optimal prediction and minimize environmental pollution is a major challenge in modern agriculture. And basically we need to consider the special variability in temporal dynamic that we've got in the orchard. When we're talking about the fertilizer and input in mature citrus orchard, where usually it's range between 150 to 350 kilogram hectare per year, and the lichen is relatively low, ranging between 50 to 150. And the meaning of those losses is usually pollution of groundwater and surface water bodies. Usually the nitrogen use efficiency in citrus is relatively low, between 30 to 60%. And therefore, one of the issues is to optimize the fertilization uptake in citrus orchard and to develop a uniform fertilization approach where we take in the single tree input in a regional scale. So when we're talking about taking the special and temporal variabilities, usually the approach of precision agriculture. Precision agriculture aim to sustainable optimization, the management of cultivars by addressing the special variability found in the crop or in the environment. And usually what we're doing is we're developing site-specific management to optimize the management area. Usually we're dividing the orchard to several management zones. And those management zones will apply different input, different nitrogen input. Usually they need to be relatively homogenized unit. When we're talking about the overall cycling of processing the precision agriculture data, so usually it's include 4 steps of gathering the data, which include information about the crop, the soil, the terrain, the climate, etc., etc. Usually we use remote sensing data in GIS or ground truthing data, processing all the data to have reasonable information from this data, and then develop a decision-making tool, and then apply this decision-making tool to see if the management we develop is actually efficient. So in this case, what we did is we took 4 citrus plots in Hefer Valley in Israel. Each plot is about 5 acres. We selected 48 sampling trees in those plots, and we developed a precision agriculture approach for evaluating nitrogen management in those citrus orchard. And the main idea is to develop them based on a site-specific, based on tree-based site-specific management. Regarding the irrigation and the fertilization, so it was relatively uniform. We make sure that the irrigation was uniform in the different orchard with the sprinklers that are in distance of ½ meter from the trees, and with the uniform fertilization in those 4 plots. And basically, we collected data that is based on ground truthing leaf sampling of different nitrogen level to assess the nitrogen level in those trees. And we use remote sensing data. The remote sensing data includes several sensors of thermal and multispectral data, which acquire bi-monthly during the year. So overall, in 2019, for example, we had 6 images, and every 2 months, we collected the data, first of all, of the UAV, and at the same day, we collected also the leaf sampling. So this is how it looks like. Those are the red points are the sampling trees, those are the orchard. Basically, what we did is we marked the location where we collected the leaves, so we'll be able to identify the trees in the imagery, and to develop based on those images and those relations a model to predict nitrogen content in the trees. We use a relatively simple sensor with 5 bands, RGB, red, green, blue, red edge, and near infrared Nicosense. And The first step was, first of all, to finalize and to develop a clustering approach. So this is a paper that we published that taking different statistical approach to evaluate the management zones. And we found in this paper that the fuzzy C mean gave us a relatively good and homogeneous management unit. And from this paper, we started working on the next one, which is dynamic delineation management zone of site-specific nitrogen fertilization. Basically, the idea is a three-stage concept, where first of all, we've got data gathering, which I will explain in a sec. Then we develop a variable selection and transformation of the scoring of the data to a scoring function. And based on the information on the variable selection, we develop a special temporal site-specific nitrogen management approach. So regarding the data gathering, so first of all, we started in developing a model that tried to evaluate the canopy end status for each tree in the orchard. It started by collecting the training data that we've got from the 48 trees during the 6 months that we collected the data. And based on the data that was collected and the spectral information, we use a support vector machine regression model to develop a prediction model of nitrogen content in the orchard for each month. In addition, what we did is we developed an envelope curve to evaluate the N content in response to yield. And based on that, we could evaluate when we are in the optimum under over-fertilization. The next step is to collect the non-constant variable, which are the N content and the canopy height, with constant variables of terrain, which related to DM, slope, and aspect. All of this information, of the constant and non-constant information, went into a transformation function based on a hotspot Getty sort statistic. Then the information plugged into a fuzzy C-mean model. And based on the fuzzy C-mean, we develop a management zones for each orchard and for each site. So basically, the non-constant variables that we're talking about are based on ground truthing and UAV data, which include the support vector machine prediction model, which is based on leaf nitrogen content, and the NDSM, which is based on photogrammetry data that basically give us the information about the crown volume or biomass. Those information were plugged into the model. So basically, we've got information for each tree, and we had tables that include for each tree the elevation, slope, northness, and content and tree height. So the results. So in here you can see the result of the leaf sampling for December 2018, 19, and 20 for the different plot, and you can see that we've got a relatively high variation in the different plot. And the next step was to develop from those leaf sampling data a geospatial model to predict the nitrogen content. So basically what we did is we collected all the information for the 48 trees with the 6 sampling date and used 16 pixels that were plugged into the model. And based on that, we developed a prediction model. The prediction model was relatively with a good accuracy of 0.7 and relatively low RMSE. And one of the things that we can see is we can see the variability that we've got between the different images. In here, for example, you can see the my image, and you can see that it's a relatively low nitrogen content, which is something that we know that in my we've got a reduction in the content in the leaves due to the phenological development of the trees. So basically what we had is we developed for each year, and in here you can see for 2019, 2020, and both years together, a support vector machine model which had a relatively good prediction accuracy and RMSE. The next step was to develop an envelope curve, which basically what we're doing is we're taking the yield versus the optimal versus the end content. And in here you can see that the area that range, that we've got the optimal value range between 2.4 to 2.7 nitrogen dry weight. And basically, those were defined as an optimal values. Over fertilization defined as 2.7 and higher, or under fertilization is defined as 2.3 and lower. So basically what we did, based on the sampling tree, we had the ability to develop a prediction model of N content for each tree. Based on the envelope curve, we have the ability to classify those values and to see where we've got in the overall area in the orchard, area where we've got an over fertilization, under fertilization, or sufficient fertilization. And you can see how it looks like for 2019 and how it looks like for 2020. And you can see that there is a large dynamic in the N content in the specific year. This was applied for October, but the variation is also during the year itself. So the next step was basically the variable selection and the transformation of the data. So we had all the information with different units, and what we did is we used the hotspot, the Getty sort statistic. And basically what we did is we transferred the data to Getty sort statistic that we've got if the relationship between the variables are significant or not. And this is the transformation of each one of the parameters to Getty sort statistic, which take into account the spatial variability of different trees in the orchard. So the data that we've got now is transformed to scoring data. The next step is to plug the information of the Z-score statistic of the 5 variables that we've got to a fuzzy C-mean model. And based on the fuzzy C-mean model, we've been able to develop the management zone. And here we tested several combinations. So first of all, we took just a constant variable, which is the DM slope northness. And the combination, the second combination include the variation in the N content during the month and the constant variable. The next combination took into account the change in the overall volume of the trees and the constant variable. And the final combination took the change in the volume of the trees and the N content and the constant variable. And basically what we had is this is the output just based on the constant variable. And when we would look on the different combinations, so the management zones will change according to the variation that we can find in the different parameters. So basically what we had is we first of all identify the variation in the management zones. And additional issue is we identify the causes that cause for those variation. And this is how it looks like. So for each month, we could see the dynamic, if we had a dynamic in the management zones. And we can also try to identify if those dynamic was related to the N content or to changes in the volume or the growth of the trees. So to conclude my talk, first of all, we developed a relatively good model for predicting N content based on multispectral sensing, which is a very nice and enable us to predict the N content for the entire orchard trees. The support vector machine regression prediction performed relatively well. In addition, the transformation of the data to the Z-score statistic and clustering delineation enable us to see the dynamic, the spatial and temporal dynamic in the orchard, and the link between yield and nitrogen enable us to identify the area where we have under optimal fertilization. And we suggest that future work should first of all focus a bit more on the relation between yield and nitrogen content to see those relationships and to finalize the threshold that are relevant for the N content. The clustering delineation could add additional inputs like water content, which could be applied with thermal sensing, sugar that could be applied with multi or hyperspectral sensing, the sugar levels in the trees, and integrated them into the into the fuzzy simile model. Of course, we can upscale this information to satellite data. Additional aspect that need to take into account is the overall nitrogen use efficiency, which basically we need to not just look on the nitrogen content that we've got in the leaf, but also to see the leachings that we've got in the soil. And in here, we selected work with support vector machine model, but additional AI and machine learning approach could be tested to see if we could improve the prediction accuracy of our model. Thank you for your attention. And if you've got any question, I'll be more than happy to answer. Thank you.